Throughout history, people of all ages have looked at the world around them and tried to figure out what's going on. Why do things do the things that they do? One of the first that we know about wrote down views of motion, why things move and why things don't move, was the Greek philosopher Aristotle. Over 2,200 years ago, Aristotle came up with his own views about motion. Aristotle proposed that there are four states of matter, or four classifications of materials or elements. He called these the four basic elements, and he said there was earth, water, air, and fire. They were layered so that earth was on the bottom, water was above earth, air was above water, and then fire was above the air. This made a lot of sense to Aristotle and to everyone around him, because all you have to do is go outside and you see there's a puddle of water, and underneath the water there's earth or ground. Above the water there's air, and if we light a fire, the fire goes up through the air. And so Aristotle said these are the four natural materials or elements, and they all have their place. They're in this order, in these positions. And the tendency of an object is to reside at rest in its natural place. So if you take an object and you move it out of its natural place, like this tennis ball, we would say this is an earth object. It's supposed to be at the bottom, on earth, not up in the air, not in water, not above the air, but at the bottom. So if I take this tennis ball and I move it out of its natural place, I've now placed it in the air. It's not where it's supposed to be. So if I release it, its natural tendency is to go back to the earth. So why does an object fall when you place it in the air and let go of it? It falls because that's what it's supposed to do. That's its tendency. It wants to fall. It doesn't want to be in the air. So the falling, that was called natural motion. An object is naturally going back to its place where it resides. Violent motion would be the motion where you take an object out of its natural place and put it somewhere else. So throwing the ball in the air is violent motion, but the ball falling back to the earth is natural motion. And everyone around Aristotle said, yeah, that makes a lot of sense. You know, anything you put up in the air, you let go of it, it comes back down. That's what it's supposed to do. Birds, they go up in the air, but they don't stay up there. They eventually have to come down. Everything has to eventually come down. Well, some people might have said, well, wait a minute, Aristotle, what if I take this log? It floats. Isn't a log wood supposed to sink and go down just like a rock does? So why do some objects sink and some objects float? Well, Aristotle could reason that if you take a rock, it's almost all just solid earth material, and it goes back to the earth. But if you take that piece of wood, that log, inside of that log there's air trying to make it go up, and there's the earth, wood, trying to make it go down, and in that tug of war, neither side really wins, so it just stays in between. And people around Aristotle would go, oh yeah, that makes sense. These objects float because they've got air in them, and the air doesn't want to sink, it wants to go up. And if you don't have enough air in it, the object will sink. And everybody's happy with that, so things go back to their natural place. Aristotle also reasoned that when an object is in its natural place, its condition, its natural condition, is to be at rest. So if I give this thing a push, it comes to a rest because that's what it's supposed to be. That's what it's supposed to do. It's not supposed to keep moving. It wants to be stationary. So it takes a force to keep an object moving, and if you take that force off, it will eventually come to a stop. And everybody around Aristotle goes, yeah, that sounds good. I mean, that's what happens. It takes a force to keep something moving. It naturally wants to stop. This object, it's not moving, but when I release the force on it, it goes back to its natural place. And everybody was happy with this. Aristotle's views of motion lasted for over 1,700 years. Everyone agreed. This is the way it is. That's a good explanation. But then in the 1500s, Galileo, followed by Newton, comes along, and they say, wait a minute, let's do some experiments. Let's see if this is right. Aristotle's view of motion would predict that heavier objects fall faster to the earth than lighter objects. Galileo did some experiments with cannonballs, not dropping them from the Leaning Tower of Pisa, as most people believe, but he let the cannonballs roll down inclines, and he found that the heavier cannonball didn't roll down any faster than the lighter one. So that went against Aristotle's views. He kept doing experiments, collecting data, and eventually Isaac Newton comes along after Galileo had already died, and Newton says, you know, Aristotle, your views, they're not right. They're wrong. And they're not just a little bit wrong, they're a lot wrong. And they're not just a lot wrong, you've got it totally backwards. You say that the object wants to stop and it takes a force to keep it going. Well, that's just the opposite. It doesn't take a force to keep it going, and it doesn't want to stop. Aristotle, you say that the ball wants to fall when I let go of it. No, it doesn't. It wants to stay there. Now, that goes against common sense because we know it falls, we know it comes to a stop, but Newton kind of argued that it only stops or it only falls if something makes it. This ball would stay in the air until something makes it fall. It doesn't want to fall, it wants to stay there. And the only reason why it falls is because something makes it. And now we all know that the thing that makes it fall, we call gravity. If there was no gravity and I let go of the ball would stay there. So it doesn't fall because it wants to, it only falls because something made it fall. It took a force to make it start moving when it was initially at rest. By the same reasoning, Newton says, no, if you give this thing a push, it wants to keep going. The only reason why it stops is because something makes it stop. Well, what is that thing that makes it stop? It's friction. If there's no friction and you give this a push, it will keep going until it hits something and something puts a force on it to make it stop. So it doesn't take a force to keep it going, it takes a force to stop it from going. So Newton's views of motion were radically different than what Aristotle had proposed and what people had believed for over 1,700 years. And this is the way scientific knowledge sometimes progresses. Sometimes we take our theories and our ideas and we make small changes over time to them. That's called an evolutionary process. But then sometimes we come up with ideas that are so revolutionary different that we make huge changes in our ways of thinking, and we call that revolutionary development of knowledge. So sometimes scientific knowledge changes by evolution, gradually a little bit at a time, and sometimes it changes by revolution. Dramatically vast differences right away. So Isaac Newton took his views of motion and he basically stated them in a law. A matter of fact, here's what happens. And Newton says, objects that are at rest remain at rest. Objects that are in motion continue in motion in the same direction with the same speed unless something makes them change. And that something that makes them change is a force. A force that's not canceled out by another force. We call that an unbalanced force, or a net force that's not zero. So it takes a force to change the motion of an object. So this idea became known as Newton's first law of motion, the law of inertia. the velocity of an object, which is speed and direction, remain constant unless acted on by an unbalanced force. Or you can say an object at rest remains at rest, and an object in motion continues in motion with the same speed in the same direction unless it's acted on by an unbalanced force. A third way of stating the law would be an object does not accelerate unless it's acted on by an unbalanced force. So any change in speed or direction is an acceleration. So that only happens when an unbalanced force acts on an object. There are a lot of different ways that you can provide examples of Newton's first law of motion. You can look up many examples on the internet, websites, or in books. I'm going to show you just a few. One example that's kind of neat that students like is you can take a little flask and put some coins on top of a card on top of the flask, and the coins are at rest. They want to remain at rest, but I'm going to put a force on the card which is going to make the card move. The coins, however, don't want to move. They want to stay there, so look at that. I really messed it up. So if you do this right, they'll fall into the flask like this. So the coins remained at where they were until the card moved, and then there was nothing to hold it up, and they dropped straight down. See, I put the force on the card, not on the coins. That's why the card moved and not the coins. Another way to do this, which is a little bit more difficult, is to take the card, put it on your finger, and put the coin on top of the card on top of your finger. You then flick the card out from under the coin, and the coin would rest on your finger. This is a little bit easier to do if you use a quarter or a nickel because they're larger and have more mass. Another demo you can do, and I've never actually tried it, is pull the tablecloth out from under the dishes. If you ever want to try that demo, it's important that you pull the tablecloth down and you use a tablecloth that doesn't have a seam on it. If it has a seam, when the seam hits the dish, it'll knock it over. So another way to do this that's not quite as daring or dangerous is just to put your object on top of a piece of paper, and then you quickly pull the piece of paper out from under and it stays. So I don't have any problem trying it that way, but I've never really done it with dishes. Another demo is the idea of if you're twirling something around in a circle, the wiffle ball does not want to go in a circle. It wants to keep the same speed in the same direction, so it wants to travel in a straight line. So whenever I release the string, the wiffle ball will move away in a straight line. So if I release it when it's right here, it will go off that way. If I release it when it's right here, it will go straight. Or however, wherever we release it, it will move off in a straight line. You can have one student standing in the middle, and you can have your other students circled around them at a safe distance away, and you can say, okay, Billy, I want you to try to make the ball go to Susie over there, and then they have to let go at the right time to see if the ball will go over there. Well, students would really have a lot of fun doing that, but sometimes that can be a little bit hazardous. So another way to do it is to tie a string to your battery-operated car, have a long string, hold the string down in the middle, and then the car will roll around in a circle. And then you could do the same thing, have the students or target spread out around in a circle and say, okay, Susie, we want you to try to make the car go over there to Ellen. And so Susie would have to let go at the right time for the car to get to Ellen. Another demo that's a little bit more daring, and you would definitely want to practice it before you do it, is to take a mass. The 500 gram mass seems to work pretty well. And I tie a thread to the top and I tie a thread to the bottom. And the question is, when I pull, which thread is going to break? Now, the answer to that question depends on how you pull. If I give it a slow, steady pull, the top thread is going to break. So see, this mass is at rest. It wants to stay at rest, but if I pull down on it slowly, I'm pulling down, so the top thread has the force of the mass itself and my pull. And those two together would be more than the force on the bottom thread, so it breaks the top. But if I give it a quick jerk, a quick pull, instead of a slow, steady pull, the inertia of this mass, it wants to stay there, it will stay there, and the bottom thread is the one that's going to break if I give it a quick pull. And it did. Now, if you practice this and you get really good, you can hold it over a student's head, but you run the risk of losing your job if the demo doesn't go right. So if you give it a quick pull, you put more force on the bottom thread than it can withstand because this mass doesn't want to move. This is the same reason why if you're fishing and you catch a fish and you jerk real quickly, you can break your line. Even if the fish only weighs 1 pound and you've got 10-pound test line in your rod and reel, you can still break it because you put more force on that than it can withstand. There are many other demos you can do and other examples. We shake umbrellas to get the water off. We put the water and the umbrella in motion. We stop the umbrella and the water tends to keep going. If you're going to stomp sand or snow off of your boots, you stomp your foot down, the floor, the ground stops your boot, but the snow keeps going, the sand keeps moving downward. This is why we wear seat belts. If you have a sudden stop, everything in the car tends to keep moving forward. So unless you're secured to the vehicle, you would keep moving forward. You can demo this by taking a doll or action figure and putting it on a toy car and run the toy car into a barrier to make it stop, and the action figure or doll would keep going forward. Then you can use a rubber band or string to tie them down and then see what the effect of the seatbelt is. So lots and lots of demos in everyday life showing how Newton's first law of motion really does hold true.